Hess's law is part of the Flipped Learning and General Chemistry series. In this video, you'll see how to calculate the enthalpy change for an overall reaction by combining a series of individual steps. After completing the assigned problems, you should understand that state functions depend only on initial and final conditions, not the path in between. You should be able to combine chemical reactions to create new balanced equations and calculate an overall enthalpy change from a series of individual steps. I'll start with a real-world analogy for state functions. A person who wants to hike from the base to the summit of Mount Kilimanjaro has to ascend a certain number of vertical feet. And this elevation change doesn't depend on the path of the hiker. A person who takes path X rises the same number of feet as the person who takes path Y. The elevation change is called a state variable. It depends only on the initial and final states of the system, not on the path connecting the points. There are many state variables in chemical systems. The subject of this video is enthalpy, but the ideas you'll see here apply to entropy, free energy, and a number of other common properties as well. Hess's law is a way to exploit path independence in a chemical system to learn something about the overall reaction X from a series of simpler reactions that start and end in the same place. We'll start with the basics of combining chemical equations. I'm showing here two chemical reactions, and I can combine together the products and reactants to describe a third reaction. The combined reactants are 2NO plus N2 plus 2O2, and the combined products are 2NO2 plus 2NO. Notice that each side has two equivalents of NO, so these molecules can be canceled from the final equation. Hess's law gives us a way to calculate the enthalpy change of a chemical reaction. Recall that enthalpy is heat transferred at constant pressure. Hess's law says that if an overall reaction may be written as a series of individual steps, then the enthalpy change, delta H, for that overall reaction is the sum of the enthalpy changes for the individual steps. This is true because enthalpy is a state function. Going back to our previous example, if delta H is known for steps 1 and 2, we can calculate the overall delta H to be 180 plus negative 112 equals 68 kilojoules. Now we'll go through the mechanics of using Hess's law. Here's a problem in which we need to change the coefficients in one of the reactions. I'm trying to get the first two steps to add up to the third, but FeCl2 doesn't cancel completely because the coefficients aren't the same in steps 1 and 2. I can solve this problem by multiplying the second reaction by 1/2. I'm allowed to do this as long as I remember to multiply all the coefficients by 1/2 so that the equation remains balanced. But what about delta H for step 2? Do I have to change this number as well? The answer is yes. Enthalpy is an extensive property, which means it depends on the amount of the substance. Delta H for a reaction is given in molar equivalents. That means 2 moles of FeCl2 reacting with 1 mole of Cl2 gives off 115 kilojoules of heat. If I divide the molar coefficients by 2, I have to divide the enthalpy change by 2 as well. Now the first two equations add up to the final equation, and FeCl2 cancels completely. The enthalpy change for the overall reaction is the sum of delta H for the individual steps. Negative 342 plus negative 57.5 equals negative 400 kilojoules when 1 mole of FeCl3 is produced from elemental iron and chlorine. Here's a different type of problem. The products and the reactants are on the wrong sides in the second equation. They need to be reversed before we can get to the final answer. It's always okay to write a chemical reaction in the opposite direction, but what does that do to the enthalpy change? The magnitude of delta H stays the same, but the sign changes. If 286 kilojoules of heat are released in the forward direction, the reverse reaction must absorb the same amount. If you change the direction of an equation, you have to change the sign of delta H. After I've done all of this, H2 cancels and the sum of the first two steps adds up to the overall balanced equation. 1 mole each of fluorine and water reacting to form 2 moles of HF and half a mole of oxygen, with an enthalpy change of negative 261 kilojoules. The last example we'll consider has a problem with phases. It looks like steps 1 and 2 add up to the final reaction until you notice that water is shown as a gas on top and as a liquid on bottom. This is a real difference that you can't ignore. Condensing a mole of steam into liquid water releases 44 kilojoules of heat, which affects the overall value of delta H. Actually, I need an 88 kilojoule correction because there are 2 equivalents of water in the reaction. After canceling the water, steps 1 and 3 add up to the overall equation: a mole of methane and 2 moles of oxygen reacting to form carbon dioxide and water. The final delta H is the sum of the enthalpy changes of the 3 individual steps, including the phase change of water. Now try this one on your own. Calculate delta H for the reaction of elemental carbon and oxygen to make a mole of carbon dioxide. In the first step, I have too many moles. I need to multiply the entire first equation, including delta H, by 1/2. The second step is shown in the wrong direction. Carbon dioxide needs to be a product and oxygen a reactant, so I reverse the equation and change the sign on delta H. Now the 2 steps add up to the final answer: 1 mole of carbon plus 1 mole of oxygen reacting to form 1 mole of carbon dioxide. The enthalpy change for this reaction is minus 394 kilojoules. So that's it. Don't forget to read the textbook sections and do the problems assigned with this video. You should come to class prepared to use Hess's law to calculate delta H for a reaction. Thanks for watching.